Radio. Looks all right. Okay. Welcome to PCTE's webinar on hardness testing. My name is Warren and I'll be presenting today. So a little bit about PCT and specifically PCTE-Industrial. PCTE-Industrial is a supplier of non-destructive testing equipment. So we supply things like ultrasonic sets, eddy current testing sets, boroscopes, UV lights, probes, specialist NDT equipment, and then of course the hardness testers. So we've got a end of financial year sale going at the moment, and specifically for industrial NDT, we're providing a free calibration block with any Equotip purchase. We're also providing a free probe if you buy 10 UT probes to the value of $220 for the free probe. We're doing a free upgrade to a 4 amp battery on our Rel Nomad UV lamps, and we're doing 10% off the ProSec FD100 flaw detector. In our other categories, we're also doing a deal on the ProSec GPR Live with a spare battery and free training for $19K. We're also offering free shipping to metro areas on equipment that we have in stock for lab equipment. For sieves, we're doing, if you buy 10 sieves, you get one free. For construction NDT, we're doing a 10% discount on the complete Profimeter range, including corrosion. 15% on video scopes that are bought with a kit in any other device, and a 5% discount and free training with any of our Pundit range. If any of those are of interest to you, please contact your local sales rep and they'll be able to give you more information on that. So PCTE, we have a bit of a special relationship with ProSec. ProSec is one of our primary suppliers for construction NDT equipment, and very recently we've included the industrial NDT range. So we've been in business for a long time, and we've got a very good relationship with ProSec. Following on from this series of webinars, we've also got Dr. Maria Felice from ProSec coming to visit us in July. So we're hoping to meet as many people as we can, and Dr. Felice will be bringing a quite an expansive kit in regards to the Equotip. So we're hoping to do a couple of good application demos with that. If you're interested in that, please contact your local sales representative. So today's webinar will be the basic side of portable hardness testing. So what we're aiming to cover is really just the essentials in regards to hardness testing, such as why you might do it, for what reason you might do it, and then the methods available to us to be able to do hardness testing. So without any further ado, we'll get started. So this is our first week, and we'll be covering the basics of portable hardness. Next week we'll be covering a bit of a masterclass. We'll be going through the operation of the equipment and also some specialist applications. Okay, so this is what we're going to cover in this webinar. We're going to cover the definition of hardness, the applications, some of the traditional methods, the portable hardness test method, which is the LEAD. We'll be covering the portable hardness test method, which is the UCI, and then the portable hardness method, which is the portable Rockwell. So we'll be providing a technical explanation, advantages of the methods, limitations of the methods, options where they're available, and then information on accessories. And then we'll cover a bit about the range, so your operating platforms from there. So hardness testing. What is hardness testing? What is hardness? Hardness is a measure of the resistance to localized plastic deformation induced either by mechanical indentation or abrasion. It's basically the resistance of the material to puncturing or scratching. It's not a fundamental physical property. It's actually a property that results of a number of interrelated properties, such as things like strength and brittleness. In terms of measurement, it's very quick and inexpensive by comparison to measure. And the hardness is in response to particular tests. Okay, yep, we're still on. However, one thing to note is that it is primarily a surface measurement. So anyone who's done work with materials know that most of the time the surface of your material will be the hardest, because that's the part of the material that cools down first. So unless you've done some treatments to sort of equalize the grain structure throughout the cross section of the material, your surface will typically be harder than your internal, than anything further towards the center of your material that you're testing. So history of hardness. Hardness really started with the Mohs scratch test. This is a test that's still in operation now. A lot of geologists use it because really you just carry a little box with the various parts of the scale, and then you do your hardness testing from there. It's a quick and dirty method. It was invented approximately 250 years ago, so it's quite a classical would be the polite way to put it. It is a relative hardness measurement, so it's qualitative, not quantitative. So you'll get you've got a scale of 1 to 10, but you know that it'll be harder than 1, but less hard than 2, or harder than 9, less hard than 10, for example. It's limited in its practical use, and there's no accurate numeric data. So it goes on a scale of 1 to 10 from talc. So 1 is talc, 2 is gypsum, 3 is calcite, 4 is fluorite, 5 is apatite, 6 is feldspar. It's a special type of feldspar. 7 is quartz, 8 is topaz, 9 is, I can't pronounce it very well, but corundum. And then 10 is your diamond. So that's where the whole hard as a diamond thing comes from. So then from there we went to stationary indentation tests. They've been in existence for about 120 years. The main methods that we use are Brinell, Vickers, and Rockwell. There are other methods around this, but these seem to be the most popular, especially in Australia. So we'll talk a bit about stationary indentation methods. So the Brinell method was invented in the 1900s. It was invented by a Swedish engineer, J.A. Brinell. It was the first widely accepted indentation test, and the hardness value is dependent on the test force and the indenter size. So Brinell hardness, so for example, your HBS is 10 over 3000, so your Brinell hardness is measured with a 10 millimeter steel ball indenter and 3000 kilograms of force. So the Brinell has swappable indenters as well for harder materials and softer materials. Another method, a very popular method, is the stationary indentation test, the Vickers, which was invented in 1924. It was a Vickers Limited British engineering conglomerate that invented it. The hardness value is independent of the indenter size. We have a pyramid diamond indenter which produces the same indentation irrespective of the indenter size. It's highly resistant to self-deformation, and indentation area is identified by a microscope. So then that provided us the added benefit of having a very small indentation. So then our hardness value is force over area again. Then we have another stationary indentation test, which is our Rockwell, which was invented in 1931. This was invented by an American engineer by the name of Hugh M. Rockwell. It's a direct measure without a microscope. The hardness value is dependent on the indenter and the test force. So we can have diamond cones, steel balls. We have various scales within the indentation test, and it's a comparison of two. So why do we even need portable tests? There are some issues with stationary testers, and the main ones are they can sometimes be impractical, slow, and destructive. So there has been a need for something that is portable and easy to use, something that we can take out onto site without having to move a material or a whole vessel or whole pipeline or something like that into a laboratory. So the first portable hardness testing method we'll talk about is the Lieb tester. So the Lieb tester was actually invented by Prosek along with the Schmidt hammer. Basically, what we do is the easiest analogy I can describe is, let's say you have a ball, and then let's take a hard material and let's take a soft material in comparison to that ball. So let's say a hard material is something like concrete, a soft material is something like sand. If you take that ball and you throw it against the concrete, you can expect a pretty high bounce back from that. If you take the ball and you throw it at sand, which is a soft material, you can expect a pretty low bounce. So if you take that principle and you apply it to a material, except in this instance we've got a indenter with a load behind it, it's pretty much the same. We take that indenter, we load it up, and then we let it loose on the material. Based on how far it rebounds, we can get an idea of the surface hardness. So we've got our impact velocity. We compare our impact velocity and our rebound velocity, and then that gives us a measurement in the Lieb scale. Now, that Lieb scale can actually then be converted over to things like Rockwell, Vickers, or Brinell. So where does it work well? Lieb is pretty dependent upon mass and thickness. So it works well on things that are heavy, bulky, and coarse grained, because it is less influenced by the vibration and the large indentation size. So those particular items are less influenced. You can use Lieb on thinner materials, but you would have to do some preparation and some maybe even coupling, but we'll talk about that more next week. Okay, so Lieb probe selection. So there are a range of Lieb probes that we can use to test to narrow down to specific applications. Your standard Lieb is going to be the Lieb D. That's going to cover most of your standard engineering applications. So usually you start off with something like a Lieb D. If you then have limited access, you would go over to something like the DC or DL. So you've got a shorter impactor to get into tighter spaces, or if it's an issue of getting the impactor right to the test surface, you can use something like the DL to get it into there. For smaller parts, you would use a Lieb C. That one has less force, so then you can test thinner items. If you've got hard surfaces, so very hard surfaces, you might go something like the Lieb E. If you need to test castings and forgings and you need more force, you might go for a Lieb G. And then if you need something that's just ultra durable and is going to last you a while, then you would look at something like the Lieb S. Okay, so then you would also consider the range of hardnesses that you're going to be testing. So you're going to consider that usually you know with the material that it will fall within a certain range, and so you will select your impactor for that specific range. So you can see in this chart here. If you would like a copy of this chart, get in contact with your local sales rep and we'll get that over to you. So another consideration with LEAB is the direction of impact. As much as you can, you want to be as close to perpendicular to the test surface as you can manage. And there are a range of accessories to help with that. So there's support rings for things like spherical concave, spherical convex, so the outside of a ball, the inside of a ball. There's also cylindrical concave and cylindrical convex, so the outside of a pipe or the inside of a pipe. There's also a universal support ring, and that one just gets you into weird and wonderful shapes. So it can do both it can do the job of some of the other rings, but also get you into some weird and wonderful places so that you can actually get a decent result out of your LEAB. So for example, something like the Z1 4.5-30 is for testing the side of cylindrical specimens with diameters between 30 and 60 mil. Another portable hardness method we have is the UCI method. It's a very popular method, one of the most commonly used portable hardness testing methods. It was invented by Dr. Klaus, I'm probably going to butcher this, Kleestattel in 1961. It's a widely established method and well standardized. So basically, what we do is we rely on the frequency of something. So we take a rod resonating at a particular frequency. We then apply that rod to the material, and then based on how hard it is, so softer materials will dampen that frequency a fair bit, harder materials will dampen it less, and you'll get a frequency shift which we can then convert to hardness or impedance. So softer or deeper or larger indentations will give you a larger frequency shift. Harder will give you a shallower, smaller indentation with less frequency shift. And the good thing about the UCI is it provides a pretty small indentation as well. So it's ideal for things like testing heat affected zones, fine grained materials, anywhere where you want to test quite close together, and also where you want a smaller indentation. So the advantages of UCI, it's a very fast and simple method. It's got a small footprint and is especially good for heat affected zones, as I mentioned. So if you needed to do hardness testing, let's say you had something like a macro and you wanted to do some hardness testing, probably not anything official, but if you wanted to do some hardness testing in the various heat affected zones, various sections of the heat affected zone, you could do that with something like a UCI because of the small indentation. You could get it close enough. So I believe it's 3 per section. And also there's less surface preparation involved. Limitation of the UCI method, it is material dependent. Every material other than steel needs a new calibration. And the results are user dependent. So constant and continuous load application is essential. So there is a bit of technique to the method, and the probe needs to be perpendicular as possible, so as close as 90 degrees. So the axis of the UCI probe needs to be as close to 90 degrees to the surface that you are testing, plus or minus 5 degrees. So in order to achieve that, we also have accessories available for the UCI probe to stabilize it and get it as close to that 90 degrees as possible. We have magnetic footing for maximum stability. We can use it on flat surfaces and we can use it on curved surfaces. So the optionally available special foot increases the measurement repeatability. We can use it for flat or curved surfaces. For curved surfaces, there are 2 different apertures. One is for 5 to 25 mil diameter, and then there's another one which is for larger diameters from 20 to 70 mil, above which you can almost consider something to be pretty much flat. One of the benefits of the Equotip UCI is that we have one probe that we can that we provide the variable load for, which can be used on various applications. So one UCI probe, you can do things as fine-grained and as sensitive as turbines. You can do something mid-range like welds, or you can do something coarser like forgings. And then the next one is a pretty interesting and exciting method, is the portable Rockwell method. So we've taken a benchtop method, and Prosec have miniaturized it. And the great thing about the portable Rockwell is that it is independent of mass and thickness. In fact, you only need to have a thickness that is 10 times the indentation depth. So it works on the same principle as stationary Rockwell. We're basically comparing two penetrations, and then that will give us our hardness. So it uses less force to make it more portable, and they slightly changed the diamond angle to make the depth easier to measure. So where would we use something like this? Thin, small, and fine-grained parts. It's a static measurement, so the reason it's good for this is it's independent of mass and thickness. So there's no requirements on the size or the weight of the material. The small indentation size fits quite well for fine-grained parts. And the good thing is, because it's independent of mass and thickness, we can actually cross-correlate it with the Lieb method, which is dependent upon mass and thickness. So we can take a series of readings and then cross-correlate them with the Lieb and create our own curves from there. So the Rockwell comes with its own set of accessories. There is a clamp adapter to allow us to apply more even force, because it is very dependent upon your force. In fact, you will, if you don't have this clamp, you will have to stand on top of it. And okay, that Siri, thanks. And you'll have to apply force from the top, and that takes a little bit of technique. You've also got 3 special feet for any geometry, so there are options available for you to get a good reading out of the portable Rockwell. The other benefit of the portable Rockwell is that it can be connected directly to a PC, so you don't need to buy, if all you're interested in is the Rockwell, you don't need to buy the 550 to be able to run it. You can actually just plug it straight into your PC and get your results from there. So applications, just a couple of general applications. If you've got some material coming in, you may want to consider cross-checking the material as it comes into your warehouse. So an incoming inspection, anything in metalworking, if it's critical for you to ensure the durability of your product, then you will want to test the hardness of things as they come in. Process control is another one. Things like heat treatment and processing shops. So to check the effectiveness of your heat treatment, for example, that is something that these are quite widely used for. And also on-site inspections. So as things wear out over time, or as things are in service for longer, they generally harden. So that can be a metric that we use to determine when we're going to swap something out, for example. And then also your inspection companies as an added service. So you would use the Lieb for things like heavy parts, roll testing of sheet. Your UCI you would use on your welds, your heat affected zones, confined spaces, anything with a finer grain structure like certain types of forgings. You would be able to use your UCI for that. And then your portable Rockwell you would use on smaller parts. So smaller parts, thinner components, anything where you need to get close together. And then the Equotip itself. So we have, with the Equotip, there is a variety of control system options. So there are things from pocket type testers to cloud-based options. So if you're going to be sending someone out and you want to be able to see the results in real time, or you want to be able to cross-check things, the Live is a good option for that. And then for your more serious or more varied applications, you would look at something like the 540 or something like the 550, which allows you to use the full range of Lieb, UCI Probes, and portable Rockwell. So the Equotip 450 comes in either a UCI specific or a Lieb D specific. The 550 gives you the full range. The Live comes in a UCI or a Lieb D. And then the two pocket type testers, the Piccolo and the Bambino, both come in Ds, in your D type Lieb and DL as well. So the difference between the Piccolo and the Bambino is really PC, your ability to connect to a PC and pull data off. Okay, so here are your major differences between the 540 and the 550. So the 540, you still get your best-in-class measuring performance in accordance to international standards. You still get a wide array of data saving and exploring features on the unit. You still get an intuitive touchscreen navigation and personalized views. Quick shift conversions for your UCI. Okay, so remembering that the 550 comes in either Lieb or UCI. And you've got default PDF reports. You've also got multi-language support. With the 550, we add things like customizable PDF reports, data export to PC via Equotip link. We can connect additional probes, so we've got the full range. So you've got things like all of your Lieb, D, E, S, G. You've got your UCI, you've got your portable Rockwell, so then you can do cross-correlation on the 550 itself. And also if you were going to test things like sheets of paper, there's also the Lieb U, which is the successor to the Paratester. We've also got automatic compensation for impact direction for the Lieb D. We've got custom conversion curves, interactive wizards, and then password protection for device lock. So if you've got if you're on somewhere where data security is critical, so something like a defense project, then that could be a consideration as well. And that brings us to the end. So next week we'll be talking more specifically about the Equotip and its applications. We'll be running